Hey there, students. I don't know how much you have ever played with magnets. I know that there's not much time in school to do things like that. I personally spent quite a few hours, I would say, in childhood playing with them. They still are fun and fascinating, especially now that they've gotten more powerful. But I want to take some time to show you how, if you've ever experienced magnets, that they show us some commonalities, because there are some things that we can learn from magnets that are most definitely true in atoms as well. And these are things that then help us to predict the way that elements behave. And that's what our next unit's about, is the elements on the periodic table and the kind of behaviors we can expect from that. So I have two magnets. They are the same size, I hope you can tell. And I have them split apart by 3 inches here. Where's my other finger? There we go, 3 inches there. And something that's kind of fun to do is just see how close do they need to be before they collide. So I'm going to take the eraser end of a pencil and I'm going to try to slowly push it together. And my hope is that you'd be able to see on this video the distance before they start flying together. So let's see what happens. Let's see if we can figure this out. Three and 2.5. Oh, it fell over. Oh well, we'll just keep going. 2 inches. Oh, there we go. So a little less than 2 inches apart, and they come crashing together. And it's fun because they're very powerful. In fact, they're a real pain to pull apart. Like if I tried to just grab them and pull, I would slip. I have to like slide them off each other. There we go. Okay, so if I was 2 inches apart, I would see that they very likely are not gonna, yeah, they're not gonna stay apart, being 2 inches apart. I have to pull them apart. So what have we learned? Well, obviously the force that pulls them together is stronger when it's closer and weaker than when it's distant. So 3 inches was distant enough. They did not have enough energy, enough force to move together. 2 inches and they start moving together. So distance seems to have an effect on things going on. Now I'm going to do something else. I'm going to make a stack of them. So I have 5 of them of the same size in the stack, and I'm going to again put that here on the 1 mark. And I'm going to try to start this one over here on the 3-inch mark like I did. And we're going to see, well, it wants to keep tumbling over. It'd be great if it had a totally flat side so I could, there we go. Okay, hopefully this is, we're going to see if there's an effect of having 5 on this side to the distance. What do you think is going to happen? You have any hypotheses? Let's see what's going to happen here. So 3 inches apart. Yep. 2.5. Whoop. Little less than 2.5, and now they come together. So what have we realized? The more magnets we have, the easier it is for them to pull each other together. The more force to pull them together we have, enough that at 2.5 now we can pull them together. Well, I hope you kind of see the similarity now between these magnets and what we have going on in an atom. In an atom we have magnets. Now I know you're like, well, we don't have magnets in an atom. Okay, you're right, we don't technically have magnets in an atom. Magnets are dipoles. There's always a positive and a negative, or a north and a south to them, okay? But in an atom, we do have things that attract. What things attract? Yeah, I hope you know, okay? So let's say this represents my nucleus. That's a proton, so it's positively charged. This represents my electron. It's negatively charged. We know opposites attract. By the way, like charges repel. I don't know if you've ever, again, played with magnets to experience this. I'm going to try and do this. I have these magnets turned up. I'm getting stuck with other magnets. I have too many magnets around. Okay. I'm going to try and get these opposite of each other and see, without them flipping in my fingers. Nope, they're wanting to flip. Okay, so I try to push them together, and I can't. I can't push them together. They will flip and stick before they, like, I can't get them close enough together with just my fingers. So opposites repel, like charges attract. So here's my nucleus, here's my electron. What's this mean in an atom? Well, this means the electrons are pulled towards the nucleus, right? And if the electron gets close enough, what should happen? Right? If the electron gets close enough, yeah, it'd run into the nucleus, okay? The atom would literally collapse in and on itself. Well, that good news is that doesn't happen because electrons are always moving around. They have so much centripetal acceleration that they won't come crashing in under normal circumstances. Would they if we get to absolute zero? Well, that's a very good question. I'm glad you asked. That would be a great thing for you to research. What does happen to matter and these electrons when you slow them down so much they can't stay away? Very interesting thing. Okay. So what do I know? If an electron is close to the nucleus, if the distance is small, it's very strong. Oh, they repelled. I had them the wrong way. Okay. If it's very close, they attract, right? Very strong force of attraction if the electron is close to the nucleus, okay? What if the electron is farther from the nucleus? Well, yeah, not so strong, right? Easier for me to just pull this away, right? If they're close, I have to put in a lot of force to pull that away. So distance most definitely has an effect in an atom, how far away those electrons are. And we know those electrons are different distances away. Will you stay away? Come on. Sorry. For all the reasons I love the new, more powerful magnets, there's also a downside to them. So some of these electrons, you know, like are in energy level 1, and then here maybe I can put an electron in energy level 2. So this was 1s, and this is now 2s, and so it's further away. And so the force between these two is definitely different than the force between these two. And I'm sure you would easily pick out, if I were to start moving this forward, which one would collide first. Okay. What if, though, I had, well, that didn't work. What if I had a bigger nucleus, as in more protons in the nucleus? I'm trying to, okay, I give up. Well, there you go. See, already, my bigger nucleus, I have more protons in the nucleus, and what do we see? We see so these are doubled here. We see that they attract even harder, just like they did last time when I had the ruler. Now this, and this is exactly what I'm trying to show. With more protons, those electrons are held closer, and I would actually expect them to be slightly drawn in, even though they're moving around fast, which I can't show here with this model. I would expect that the electrons are going to be pulled in slightly closer to the nucleus because of the greater amount of protons. So this would be like 4 protons here, and it definitely has a lot more force than when it was just 1 proton. It shrinks the distance pretty quickly. So really great thing is there is a mathematical equation that tells us all about this. We call it Coulomb's law. And Coulomb's law works great for magnets. Absolutely beautifully predicts mathematically what's going to happen to magnets. What does Coulomb's law entails? Well, it entails amount of force, like 4 is greater force than 1, and it entails distance. So the farther they are away, the less force of attraction there is, and the closer they are, the more force of attraction there is. And not only does Coulomb's law work great for magnets, it works great for atoms, and it works great even gravity. Coulomb's law allows us to mathematically calculate the gravity between things, like us and the sun and us and the moon and things like that. Even your body specifically and the earth, we could use Coulomb's law for. So very predictable patterns that we can learn by playing with magnets. I hope you have some point in time in your life played with magnets. If not, like maybe for Christmas, ask for a neat little $10 set from Amazon of some of these neodymium magnets. Get different sizes, maybe different shapes, and just have some fun with them. Okay. Whether or not you do, that's on you. You will just miss out if you don't. But we're going to talk about how this is going to actually play out in atoms in our work. So we're done with the little video. Hope it was good for you. Catch you in a moment.